Alright, so in the last video we stopped right around talking about density connected points, and I just wanted to briefly mention this is the kind of output that you get from a data set. And so what you're looking at here is data in the shape of kind of a horseshoe with like a square or circular shape inside. And so this problem would be very difficult for something like k-means to handle. It might be interesting to see neural gas. See, the problem with neural gas is when is trying to determine this epsilon. This is a really close epsilon here, and so we might have trouble with neural gas because of those the closeness of the two clusters. But DBSCAN, of course, it's taking a really nice it's doing a really nice job clustering, and so the MATLAB version of this will output the title with the epsilon and the minimum number of points that we used. So that way you can capture all that information in the picture. Good. So this is kind of the thing that we're after, right? We're identifying noise, and then we have the two clusters. So here's the noise points. Oops. And then you know what's missing from the data from this is any kind of cluster centers, though, right? And so that's kind of unfortunate. But we do have every data point then in this data set is classified then as noise cluster 1 or cluster 2. Good. And by the way, the number of clusters is automatically set by these two parameters. So changing those two parameters, you're going to get a different number of clusters. All right. So how does this how does this algorithm work? This is a nice image here. I got it from Wikipedia. Sometimes Wikipedia is good. And this is one of those examples. So the reason I say that is because suppose that you're at the point A and you're trying to see where all the core points are. So if you're starting at A with, let's get a different color here. If you're starting at A here, whoops, you see that with minimum number of points equal 4, then A is a core point, right? And so what we would do in the algorithm is we would then look at the points in this neighborhood and see where its core points are, or see where what is in its neighborhood. And so this is also a core point, right, by itself. So that's not a border point, right? That's also a core point. And so you would then look at its neighbors, right? And so we would end up at C here. This is a boundary bar border point, right? Okay, but C would still belong in this set here if we're including all the points within epsilon of the core. And then you just continue that process. So we would also be looking at this epsilon neighborhood. Lots of data points there, so those would all be included in the cluster. And then you would look at this cluster point here, look at its epsilon neighborhood, and pull in all of its points within the epsilon neighborhood as part of the cluster. And then this one is not a core point, but again, it's a cluster point of this point, or a core point. It's a border point of this point, right? And so therefore it would be included as part of the cluster. And so this is how the cluster expands by just using a single core point. You just go through and you just start collecting all the points that are within the epsilon neighborhoods. And then if a point is by itself in isolation here, well, it doesn't have to be in isolation. It's just less than min points and not a border point, right? I don't know why my thing is doing so. Oh, I've got it on pencil instead of pen. Sorry about that. That might be a little bit sharper. Okay, so then this would be a noise point. But one thing I should say, even though we were kind of making a big deal about border points, the output of the algorithm doesn't actually tell you what points are border points, although you could tell pretty fast. All right, so let's take a look at the algorithm then in pseudocode. So for each point in X, if X is not yet classified, then if X is a core point, collect all points density reachable to X and assign them to a new cluster. So this is what I mean by, this is the expansion, right? Once you hit a core point, you just keep expanding the data points in that cluster until you run out. The other points are going to be assigned to noise. Notice that border points aren't specifically dealt with in here. They are if we had a little bit more complicated pseudocode. I wanted to try to keep this as simple as humanly possible. But this is actually how the algorithm looks. So if you look at MATLAB, you'll see how this works. There's actually two main pieces of code. One is to do the expansion, and one is to check to see how many points or which points are within epsilon of a point, given point. Good. So DBSCAN is kind of nice because of these theoretical results. Number one, for all points PQ in the cluster, P and Q are density connected. What? Is that true? That's amazing. So this is a nice feature about the clusters in DBSCAN. This is a nice representation of them. And then given a cluster C with an arbitrary core point P, right, the cluster C is the set of all points density reachable from P. Right, so if you start with an arbitrary core point P and you start looking for all the points that are density reachable, remember that's directly density reachable or just density reachable. You're going to start collecting all the points within a given, you're not going to be able to see that, within a given cluster. Yeah. And so that's how it's building the clusters, is through this idea of density reachable points. Okay? And then points that are not directly density reachable from at least one core point are classified as noise. And that's what we were talking about in the picture up here. Yeah, this point is not directly density reachable from any core point, any of these core points. So therefore it's noise. Good. And that is the algorithm in a nutshell. There are some rules of thumb. I will let you read through those rules of thumb because I don't like to, well, I guess, do you want me to read to you? Well, this is a really nice example. That's why I included it in here. You can see the original data set, right, has some really thick clusters of points, and DBSCAN did a fantastic job separating those. This is an example where DBSCAN may fail completely, and we're going to try to replicate some of these failures in the lab, because you're going to have to adjust your parameters until you get a fairly reasonable clustering. And so, this is a good clustering on the left, but on the right, most of this has been, all this stuff right here has been classified as noise. And so the algorithm is focusing in on these density rich regions and ignoring the rest. And so epsilon should be as small as possible just in general. And there's some ways of getting an estimate for the minimum number of points, but basically it should be twice the dimension that your data set is. If you don't have at least twice the dimension, you might be in trouble. You might not have enough data to really accurately set the clustering. Yeah, this value is highly dependent upon the problem. Yeah, there's some scaling issues that might occur. We'll talk about comparisons after you've had a little bit of experience with at least NeuralGAS and DBSCAN, since we've already talked about the k-means. All right, so read over the rest of those, try out the homework problems, and I will talk to you later.